All right, so in this video, we're going to talk about mass spectroscopy or mass spectrometry and how it relates to isotopes and average atomic mass. So when we take a look at the periodic table and we look at each element, you'll notice that most of the masses are in decimals. So lithium is 6.94. Well, we know that when we get the mass of an atom, it's just protons plus neutrons, so you can't have a decimal point for that. The reason that it's a decimal point here is because it's an average. It's an average of all the isotopes that we have together. So let's just kind of refresh on average atomic mass really quick. So average atomic mass is not just a normal average. So you're not going to simply take up the masses, add them together, and then divide by how many ever isotopes you have. It's a weighted average. So that means that you have to take the percent of each isotope into account. So to get the average atomic mass, you're going to take the mass of the isotopes, multiply it by the percentage as a whole number, and then divide by 100. Now, if you wanted to, you could take the mass and multiply it by the percent as a decimal, but don't divide by 100. Just do one or the other. So let's do this really quick, just to refresh. So neon has 3 isotopes of masses 22, 21, and 20. If the isotopes have the abundance of 8.01, 1.99, and 90, what is the average atomic mass? Okay, so now just take the mass of each isotope, multiply it by the percentage, and everything goes in order here. 21 by 1.99, and then 20 by 90. And then multiply, add, and then divide by 100. So at the end, I'm going to get 20.18. Now, if I'm looking at this, I'm also going to know automatically that the mass, the average atomic mass, should be closer to 20 since it's got 90% of it is going to be 20. Okay, so a mass spectrometer is going to be used to identify compounds, and also helps you determine the chemical composition of a substance. This can be found in almost every single lab that exists. And basically what happens is you take a sample, okay, so you take it, you heat it up to a very, very high heat, so you're going to vaporize it, and then the gaseous atoms are then ionized. So usually we take a beam of electrons, aim it at the gaseous atoms, and then that will in turn knock off an electron of the gaseous atoms and create a cation. So, and sometimes it can be ionized in different ways, but a beam of electrons is typical. After that, we're going to take these gaseous ions now, and then it's going to be accelerated through a tube, and then it's going to go through a magnetic field. Well, then all those ions are going to be sorted by their mass to charge ratio. So if all of your ions have the same charge, then really you're just sorting all these little pieces by mass. So if we're just looking at an element, we're going to sort all our ions by their mass, and we're going to see the different isotopes that we have and how often they appear. So that's how we get those numbers. So this is what a mass spectrum looks like. Now, they can be much more complicated than this if we have like a compound, but in the scope of this course, you're just going to be looking at elements. So when we take our sample and then we put it into the device, this is the spectrum that you're going to get back. So on the x-axis, you're going to have the mass to charge ratio. It might say m/z or mass number. So really it's going to tell you the mass. On the y-axis, you're going to have either percentage or abundance. So this just tells you how often this appeared. So I can tell, well, I have a mass of 65 here, so my copper 65 appeared at a lower rate than my mass of 63. So right here, if I go to the y-axis, it's about 30. It's about 30% or 31%, and then this one is about 69%. So copper 63 appears 69% of the time, and copper 65 appears about 31% of the time. So essentially what you're doing is you're getting the mass of each isotope, and then you're getting the abundance. This is how we get these numbers. All right, so let's look at a mass spectrum. So let's look at chlorine. So I want to know how many isotopes are indicated here and which isotope is more abundant. Okay, so now when I look at this, I do have 1, 2, 3, 4, 5 peaks. And normally when you see all those peaks, you'd say, okay, I have 5 isotopes. However, be careful about this because chlorine is special. If you remember, chlorine is diatomic, which means essentially when I take the chlorine in the very beginning of the process, it's usually going to be a diatomic molecule. So you're going to see peaks appear at the mass of 2 atoms bonded together. So if I'm looking at this right here, just know isotopes, when you're looking at the mass, they're not going to be double the mass. That's not going to happen. They can be, maybe 5 to 10 more, depending on how large your atom is, of course, but it's not going to be double the mass. Okay, so double the mass indicates that you have something that's bonding together. So I have here, for each atom, okay, I have 2 isotopes. I have a mass of 35, and then I have a mass of 37. I only have 2 isotopes here, even though I have 5 peaks, because these peaks represent the diatomic molecules that you'll see. Well, why do we have 3 peaks for that? Well, we have 3 different combinations. So we could have a mass of 35 plus another 35. So this is a chlorine atom that weighs 35 or has a mass of 35 plus another one that also has the same mass. And then I could have 35 and 37, and that would give me 72. And then technically I could also have another one, 37 and 37 could combine to give me a mass of 74. So that's why you have the 3 peaks here, because you have 3 different combinations. Now I want to point out something. Okay, let's look at bromine. So here's the mass spectrum of bromine. And again, we know that bromine is also diatomic. So we do see that, that the spectrum where we have the diatomic molecules showing up. Now, I wanted to point out something about this. So we have a mass of 79 and we have a mass of 81. So they're about equal. But if I look over here, that peak in the middle is much more common than the 158 and the 162 molecule. Okay, that's because of statistics. So the 158 peak would represent a 79 and a 79 coming together. Okay, the 162 peak would be an 81 and an 81. Now, the 160, obviously, yes, it's going to be the 79 and an 81. But technically, okay, statistically, I also have this combination, even though I know it's the same number set. But this is more about statistics. So you're going to see this one appear more because technically you have different ways that it could come up. Okay, so let's calculate the average atomic mass with a mass spectrum, which you could be asked to do. So I have a mass of 10 and I have a mass of 11. So I have 2 isotopes here. But if I look, I have a relative abundance of 100. Okay, and then I also have 20 here. So this is 20 and this is 100. Now the reason that happens is because when it goes through the device, it's going to set one of them at 100. That's what abundance is. So really you can still calculate a percentage though. So for the one at 11, or the one that has a mass of 11, I have 100 out of a total of 120. That would be my percentage right there. And then this one, I have 10, the mass of 10. Okay, so there's 20, it appears 20 out of a total of 120. Okay, so if you're given a relative abundance, and you'll notice that if you have that, well, first of all, it says abundance, Second of all, like you're going to notice, well, I have 100 and then I have something else so they're not going to add up to 100. No. When it gets pushed through the spectrum or when it gets pushed through the detector, it takes the one that appears the most and it sets it at 100. That's what the device does. So once I do this, I'm going to get 10.82 or 10.83. Now something to note, 100 divided by 120, that's going to give me 0.616, 6 some change. And then this one gives me 0.833. Okay, these are already in a decimal format, so I don't need to divide by 100 at the end because I'm multiplying it by the decimal. Okay, so let's look at an AP question. So what could you potentially see on the exam? Well, here's a multiple choice question. It's giving you the mass spectrum. And then it's saying the mass spectrum of element X is presented in the diagram above. Based on the spectrum, which of the following could be or can be concluded from about element X? Okay, so if I'm looking, I've got 1, 2, 3, 4, 5 peaks. They're relatively close, so I can't assume that I've got a molecule or anything like that. So let's look at the answers. Because usually with a multiple choice question like this, you can eliminate a lot of answers right off the bat, or at least half. So X is a transition metal. Okay, well, if I go pull up a periodic table, it's possible that this could be a transition metal because the masses are in this range. Okay, and each peak represents the oxidation state of the metal. Okay, an oxidation state has nothing to do with mass. Okay, so if we're talking about an oxidation state, that has nothing to do with this mass spectrum. So automatically, I can just eliminate that. B, X contains 5 electron sublevels. Again, this diagram is showing you the mass. This has nothing to do with the electrons, okay? So if it contains 5 electron sublevels, I can maybe tell that with a PES diagram, but not with a mass spectrum. So that is not going to be the answer. The atomic mass of X is 90. Well, it's going to be very close to 90 because I do have an isotope at 90. That's high. It's about 55%. But it should, remember, I've got to account for all these other isotopes, so it's probably not that. Now, the next one says the atomic mass of X is between 90 and 92. Well, most of my isotopes weigh between 90 and 92, so I could probably definitely conclude that without even going through and calculating that. If I really wanted to, I could calculate it, but it just seems time consuming. And also, this multiple choice question, you're not going to get a calculator. So I would go with elimination here. Okay, so now let's look at this one. This is actually the same mass spectrum. It just looks a little bit different. And it's asking which of the following is the identity of the element. Okay, so let's pull up a periodic table. Okay, so if I look at Y, because let's use our multiple choice answers here, it's 88.9. I don't see anything here below 90. So it cannot be Y. If it was Y, I would have some peaks below 90 here. So let's look at ZR. Okay, so ZR has a mass of 91.224. Well, the average mass is in between 90 and 92, but let's see if I can eliminate any of the other choices. So MB is 92.9. It's pretty close to 93 then. I don't even have a peak at 93, and most of my peaks are below 92 or 92 and below. It's probably not that based on that. And then TH, or thorium. Okay, so thorium is, where is it? Right here. It's actually in the F block, and its mass is 232. Well, that is definitely not going to be this spectrum because it's too heavy. So it's definitely not that. And so it has to be B, zirconium. Now, I just want to point out something about the periodic table. Sometimes you'll see the elements in parentheses like this, like the average atomic mass. That's because it has one stable isotope. So that is something that you could use to help with a mass spectrum question too. So if it shows up as like radium is 226, it only has one isotope that's stable, which is 226. So if I had a mass spectrum, I'd probably only going to see one peak at 226, and that's it. Okay. All right, so I just wanted to show you a few examples of actual AP questions because these are two questions that have shown up on exams in previous years. So, all right, and that's that.